This is AI Papers, a deep dive. We start where the work starts, the abstract, the method, the experiments, and we don't skip the parts that matter. Okay, let's do this. Here's a result that should bother anyone building AI agent teams. You take one strong language model, hand it a task, it scores a number. Then you do the supposedly smart thing. You split the job across a team of specialists. A manager that routes the work, a few domain workers, a responder that assembles the final answer. And on the metric that matters most, the team does worse than the single model working alone.
Quick heads up before we go further. This is an AI-made explainer, both voices included.
This paper takes that failure and builds a fix, a way to look at a broken team of agents and figure out exactly which member dropped the ball, then rewrite that member's instructions. On one model, it nearly doubled the score the team had been failing. A measure called joint goal accuracy climbed from under 30 to over 54.
And here's the hook that runs under the whole episode. The same method, on the same task, with a different model underneath. It didn't just fail to help, it collapsed the system. One backbone's success rate fell from 71 to 7. Same tool, opposite outcome.
So by the end, you'll understand how you can backpropagate blame through a team of chatbots, borrow the single most successful idea in deep learning and point it at agents talking to each other in plain English, and why getting that blame right turns out to be the entire game.
Why should anyone outside this little subfield care? Because if agent teams really are how we'll build AI systems, the practical pain is debugging. When the pipeline fails, you have no principled way to know whether the manager misrouted, a worker hallucinated, or the responder dropped half the answer. This paper's bet is that the bottleneck isn't the thing doing the fixing. It's the blame signal feeding it.
Let's start with why the teams fail at all, because it's not subtle. There's recent work, Pan and colleagues last year, literally titled, "Why Do Multi-Agent Systems Fail?" And the answer is the boring human stuff. Bad handoffs. One agent assumes another already handled something. Information gets omitted between steps. Weak verification at the end. You decompose the task for division of labor, and the coordination overhead eats the benefit.
And the authors give this old problem its proper name: credit assignment. It's one of the oldest headaches in reinforcement learning. You win or lose a game after hundreds of moves, but which move actually mattered? Same shape here. The final answer is wrong, and all your optimizer is told is, the team lost. It's a relay race where you drop the baton, lose, and the only feedback on the scoreboard is the final time. You can't fix the handoff you can't locate.
Which is the whole frustration. If I tell you the baton slipped on the third exchange, you go drill the third exchange. If I just tell you that you lost, you've got nothing to act on.
Right, and existing optimizers for these systems, TextGrad, DSPy, GPT Swarm, that whole lineage of treating an LLM pipeline as a program you can automatically improve, they mostly work off that global verdict. The whole system gets one grade. Nobody's pointing a finger at a specific runner.
So the move this paper makes is to steal the finger-pointing machinery from deep learning itself. Finn, this is your half. Walk through what they actually built.
So the method is called gradient-based connections, and the core reframing is almost simple. Think of the team as a graph. Each agent is a node, a prompt plus a model. The arrows between them are information flowing. Agent A's output becomes part of Agent B's input. Agents fire in order. Last one gives the answer. Standard stuff so far.
That's the picture on screen, the boxes and arrows, a pipeline.
Here's the twist. In a normal diagram, that arrow from A to B is just binary. A feeds B, yes or no. GBC says that's not enough. The arrow should carry a number telling you how much B actually cared about what A said. And to get that number, they reach for gradients.
And before you say gradient 40 more times, give people the handle.
Fair. A gradient answers exactly one question. If I jiggle this input a little, how much does the output change? Big gradient, the output is very sensitive to that input. Small gradient, the input barely matters. That's the whole job it does here. It's a sensitivity meter. Nothing more mystical than that.
So they point the sensitivity meter at the connection between two agents.
Exactly. They ask, if I perturb what the upstream agent said, how much do the downstream agent's word choices shift? Picture a round table where everyone speaks in turn. You want to know who actually influenced the final decision. You measure it by checking how much the next speaker's words would move if you'd altered what the previous person said. Someone whose remarks barely register scores low. Someone whose every word reshapes the response scores high. That influence score becomes the weight on the arrow.
So now the graph isn't just who feeds whom, it's who feeds whom and how loudly.
And once every arrow has a weight, they prune. For each output, they keep only its single loudest predecessor, top one by default. That turns a dense tangle into a clean blame graph. Then they attach the error to the final node and trace backward, the way backprop walks blame back through a network. You start at the failure, follow the strongest arrows back, and build what they call attribution trajectories. Chains that say, this wrong answer traces through that output, back through this one, to this specific agent.
Watch that on the diagram. The error lands on the last box, then lights up a path backward through the graph, arrow by arrow, until it stops on the agent that owns the mistake. That path is the blame report.
That's the hero of the whole system, right there. The error flowing backward along the loudest connections until it names a culprit.
Now, one thing I want to nail down because the title is a little seductive. Gradient-based. Are the gradients actually fixing anything? Are we doing gradient descent on chatbots?
No, and this is the most important clarification in the episode. The gradients only do diagnosis. They tell you which agent to blame. The actual repair is done by a completely separate LLM optimizer that reads the blame report and rewrites the offending agent's prompt in plain English.
So it's an MRI and a surgeon.
That's the cleanest way to hold it. The gradient attribution is the MRI machine. It locates the injury with quantitative precision. The LLM optimizer is the surgeon who reads the scan and decides how to operate. The machine never performs the surgery. And what the surgeon mostly does, concretely, is append a little warning section to the agent's prompt. Something like, you keep missing this tool call, here's an example, watch for it. With a real failure attached.
And the error signal it's working from isn't a number either, right? It's words.
Right, they call it a verbal loss. Instead of a numeric loss, it's a structured natural language critique. On the dialogue benchmark, it literally lists the slot value pairs you got wrong. Here are your false positives, here are your false negatives. That text is what gets attached to the final node and traced backward. So the whole pipeline is feedback in English, diagnosis by gradient, repair in English.
I want to flag something here that comes back to bite us later. What they show cleanly is on one model backbone. The method is identical across models, but as we said up top, the two backbones go opposite directions. Hold on to that gap. It matters.
It matters a lot. But let's earn the surprise properly, because the technical core is the part that actually pays off.
So here's the gear shift. The densest stretch is how they turn those per-word sensitivities into one number on the arrow. And there are 4 ways they tried it. Stay with the picture because the payoff is a genuine reversal. The version that theory says should win loses.
There are 2 choices, stacked. First choice. When you've measured how loudly an upstream output drives each downstream word, how do you summarize it? You can average the loudness across all the downstream words, call that mean loudness. Or you can take just the single most influenced word, peak loudness. The idea behind peak is that most words are noise. Only the moment of maximum influence carries the real signal.
So mean versus max. Broad influence versus the one loudest spike.
Second choice is subtler. Do you use raw loudness, pure sensitivity? Or do you weight it by how big the upstream word's own value was? That second one is a known interpretability method, gradient times input, from Srikumar and colleagues back in 2017. Roundtable version. Instead of just, how reactive was the listener to this speaker, it's, how reactive, scaled by how substantial the speaker's own contribution was.
So loudness versus loudness times importance. And those two choices cross, giving you 4 variants total: mean loudness, peak loudness, mean loudness weighted, peak loudness weighted.
4 variants, nearly identical names, and the difference is the entire empirical heart of the paper. Because here's the thing the interpretability literature would tell you. Gradient times input usually gives cleaner attributions for an individual prediction. The value weighting cancels noise. On paper, the loudness times importance variance should win.
And they don't.
They don't. The 2 pure loudness variants, the L1 norm ones, raw sensitivity, no value weighting, win on both axes, best at correctly identifying the responsible agent and best at the final task performance. The intuition the authors offer is that across agents, in this messy crosstalk setting, raw reactivity, how hard does the upstream output drive the downstream generation, is just a better blame signal than the polished value-weighted version.
And that's the line worth slowing down on, because it's the real intellectual payoff, not the benchmark number. The finding underneath the 4 variants is this: attribution quality predicts optimization quality. The 2 variants that point at the right agent most accurately are the same 2 that produce the best fixes. Get the blame right, and the fixing follows.
Which flips where you'd think the difficulty lives. You'd assume the hard part is the optimizer. How cleverly do you rewrite a prompt? This says no. The optimizer's the same LLM in every case. What changes the outcome is whether you handed it the right culprit. The bottleneck is the diagnosis, not the treatment.
There's also one engineering wrinkle worth a single sentence, because long prompts make this expensive. Since the attribution only needs gradients on the input, the upstream text, and the agent's own prompt is fixed, they freeze the prompt as a cached prefix. Read the boilerplate once, snapshot it, only spend gradient memory on the part that varies. That's it. It just keeps the thing runnable.
So, to consolidate before we look at whether it works. Teams of agents fail because nobody can localize blame. GBC weights every connection by real influence, traces the error backward to a culprit, and lets an LLM rewrite that culprit's prompt. And the surprise is that plain loudness beats the fancier value-weighted score as the blame signal.
So does it actually work? Here's the anchor result, and it's the clean one. The benchmark is MultiWOZ, task-oriented dialogue, a manager routing to domain workers to a responder. On the Qwen backbone, that joint goal accuracy I mentioned at the top, basically, did the system get the user's full set of goals exactly right, went from 28.9 to 54.4.
Roughly doubled.
Roughly doubled. And the secondary measure, slot F1, how many individual facts it pinned correctly, went from 79 to 91. If the theory holds, the team should go from worse than one model to best in class. And it does. Afterward, it's posting 99 on Inform and 94 on Success, the strongest system overall.
And the before picture is what makes that satisfying. Before optimization, that Qwen team was a perfect illustration of the puzzle. It actually had higher Inform and Success than the single agent, but much lower joint goal accuracy. So it sounded fluent and helpful while getting the user's actual goals wrong. The team was worse in precisely the way that matters.
The second benchmark is Tau Bench Retail, multi-step tool use. The agent has to make correct tool calls and produce complete responses. Harsh metric. The overall reward is the product of getting the actions right and the output right, so you need both. There, the peak loudness variant lifted Qwen from 13 to 24.3, and that edges past the strong single-agent baseline of 22.6.
Which is the bar that actually counts. Beating your own single model, not just beating your broken team.
And notice which agents got rewritten most. The domain-specific workers, far more than the manager or the responder. That lines up with the error analysis. The failures were cross-domain confusion, information omission, over-prediction on the dialogue task, and retrieval failures on the tool task. The blame consistently landed on the workers, and the workers are where the errors were.
Okay, now I have to be the one who pulls on the thread we flagged earlier,
because the paper's own tables hand it to us.
Go.
The improvement story is, to a real degree, a Qwen story. Everything we just celebrated, the doubling, beating the single-agent baseline, that's the Qwen backbone. Run the identical method on Llama, and on MultiWOZ, the same pure loudness optimization that healed Qwen crushed Llama. Inform fell from 84 to 42. Success from 71 to 7.
From 71 to 7.
Same method, same task, same blame signal. The only thing that changed is the model underneath, and one backbone got fixed while the other got gutted. And the surgeon analogy is exactly why. The repair isn't a clean protocol. It's an LLM heuristically rewriting prompts, and that rewrite interacts unpredictably with whatever model has to follow it.
So the honest read is the headline, "Improves multi-agent performance is stronger than the model-by-model evidence, where one of two backbones often regresses."
And it goes deeper than backbone variance. Two more things a sharp reviewer flags. First, gradient-based is doing some metaphorical work. The gradients only choose which predecessor to blame. There's no ablation that isolates attribution-guided optimization from just running the same LLM optimizer with a decent verbal loss and random blame. So we don't actually know how much of the gain is the gradient attribution versus the optimizer being competent on its own.
That's the one I'd most want answered, because the whole pitch is the blame signal is the bottleneck, and the cleanest way to prove that is to wreck the blame signal on purpose and show performance drops.
And second, even the central correlation, attribution quality predicts optimization quality, rests on comparing 4 formulas across 2 models. That's a handful of points. Suggestive, not a law. And attribution accuracy itself is measured by a coarse proxy. Did the blame trajectory contain the workers responsible for the dialogue's domains? That checks domain coverage. It never directly validates the token-level precision that motivated the entire method. The fine-grained blame is the selling point, and it's the one thing they don't directly verify.
I'll concede all of that. 2 benchmarks, 1 architecture family, 30 training samples, 10 optimization steps, no confidence intervals. This is a first-order method on small sets, and the authors say as much. They're upfront that gradients here might miss the complicated non-linear ways agents tangle together over long workflows.
And it's not free either. A full 10-step run is hours, not minutes. Llama roughly twice as slow as Qwen. So it's an expensive diagnosis that sometimes prescribes a fatal treatment.
But, and this is where I land, the reframing survives all of that. Even if this particular implementation is narrow and brittle, the durable idea is clean. Stop pouring effort into the optimizer and start measuring whether your blame signal points at the right agent. That's a transferable principle no matter what you build the agents out of.
It is. The seductive mental image, gradients flowing through a whole team of chatbots, end-to-end, tuning everything. That's the wrong picture, and I think the title invites it. What they actually did is humbler and honestly more interesting. Borrow gradients purely to locate the failure, then hand a plain English fix to a separate model.
So here's the takeaway bigger than the method. For years, the work on optimizing LLM pipelines has poured into the fixer. Smarter ways to rewrite prompts, compile programs, search the space. This paper makes the case that the real lever might be one step earlier, the quality of the diagnosis feeding that fixer. Get the blame right, and the fix is comparatively easy. Get it wrong, and your best optimizer collapses a working system from 71 to 7. The bottleneck in optimizing agent teams may not be the surgeon. It may be the scan.
Which leaves a genuine fork. Do we keep investing in sharper blame signals? Better token-level attribution flowing backward through these graphs, the path this paper bets on? Or is prompt editing on top of frozen models a dead end? And the real move is to actually train these agent systems end-to-end and stop diagnosing by metaphor. If you've shipped one of these pipelines, you already have a gut feeling about which way it breaks. Drop it in the comments and say why.
The full annotated version of this episode is on paperdive.ai. Every technical term tapped to define, with links to the related papers grouped by theme, the textual gradient lineage and all, plus our weekly and monthly roundups.
Quick housekeeping. This script was written by Anthropic's Claude Opus 4.8. Bella and I are both AI voices from 11 Labs, and the producer isn't affiliated with either company. The paper is GBC, Gradient-Based Connections for Optimizing Multi-Agent Systems. Posted June 26, 2026. We're recording 3 days later.
Find the agent that dropped the baton before you try to fix the team. See you in the next one.